folks. Here's our first pre-recorded content video. This content is based on the material that's in chapter 2 of our text. The publisher PowerPoint is entirely comprised of images and figures from the textbook. There's very little, very few slides deliver any content except the captions of the figures. So if I haven't posted the publisher PowerPoints, I will already, or I will very soon, I mean, but I'm not, and they're going to need some editing. So take them with a grain of salt. I encourage you to pair this video with the text itself, and then to pair it with the demo and progress activities that we do next in class. So without more intro, let's dig in. We said that the three sort of fundamental things that humans can perceive about their reality: space, time, and matter, right? How much space is there, how much time has gone by, and how much stuff is around me or represented by that object over there or whatever. If we're going to make those measurements about space and time, well, time, we said, was the way that we track how things change. So we're looking at the space around us and observing changes in that space, which usually means that a thing which existed somewhere now exists somewhere else. It has moved. Motion is like the very first thing that we'd like to try to describe and communicate to each other about. Think back to early human civilization. Coordinating a group activity like hunting for food requires an understanding of and an ability to communicate about motion that happens at different times. So this need is very biological, the ability to, and the skill with which we can communicate about motion. If we'd like to do that, we should be quantitative about somewhere. This word that means the place where a thing is, but we should be a little bit sort of precise about the way we communicate. So we have to define some things. Let's define position, and that's the location in three-dimensional space of some object in order for that to be useful, it has to be relative to some point of reference. Relative to some origin. In this room, when I'm recording videos, the origin will almost always for me be the bottom corner of the room over here. Once we start talking about 3 dimensions, the x-axis will point along the wall with door on. The y-axis will point along the wall with the whiteboard, and the z-axis points up the room. So As we look at the corner, Z goes up, Y goes along the wall to the right, and the X-axis, as the X coordinate increases, we're moving along the wall away from the door towards the wall behind the computer here. So this line here is like coming out of the page at our face. And we could track some position, some spot. According to its X, Y, and Z coordinates in that space. If I started from the origin, in order to get to that spot, I'd have to follow this direction. And that direction from here go there in this direction, this far. I'd like that to mean position. So that's the sort of picture that represents the idea we just defined. Because it has a size, you got to go this far and a direction. There's only one direction I can go from the origin that'll get me to that spot in space. We say that this is a vector quantity. It is a quantity with magnitude or size and direction. For now, as we're just getting started describing motion, I'd like to restrict ourselves to motion back and forth, just motion in one dimension. So like, ignore the fact that there is the Y and the Z. Let's just talk about the X direction. Motion towards the wall and back away from the wall, towards the camera and away from the camera. That's all we'd like to talk about. One dimension only. So if we are somewhere along the X-axis, we can specify where we are away from the origin with the X coordinate. So the variable that I'd like to use, the symbolic variable that I'd like to use to represent the idea of position, is X. Since we're somewhere along the X-axis, the X coordinate will do a perfect job of describing where we are relative to the origin. Okay. Suppose our position changes, which is kind of what we'd like to talk about. We'd like to talk about motion. I'd like to define two versions. Why do we need two versions? Well, okay. Suppose I start from here, I move to here, and then I move back. Overall, my position hasn't changed, but I did move. And if we did this trick in a car, like in a little bit, I'm going to get in the car and drive to campus, and then later turn around and drive back. My overall position from now until later this evening won't have changed, but my car will definitely say that I moved. The odometer will track the miles between here and campus. So there's two different flavors of changing position, one cares very much about the actual position and how it changes, vector quantity. And the other cares only about kind of how many steps did you take? How much distance did you travel? And that's the word I'd like to use, is distance. So for changes in position, I'd like to define two things. Displacement. And that's the vector kind, the kind that cares which way we go. And if we start from somewhere, go elsewhere, and come back, our displacement overall is 0, because the position has not changed. This is quite literal. Change in position. If the position is later what it was before, then there is no displacement. Never mind that we might have gone to the moon and back. Distance traveled. Displacement only compares one position to the previous position. That's it. Change in position. I'd like to use the same symbol X because we're talking about position, but this idea change, it's going to come up again and again. And I'm going to use a symbol for that, this capital triangle, delta. So delta X, change in what? X, that's position. Delta is our sort of shorthand, our variable or symbolic shorthand for change in whatever symbol comes after it. If I start at x equal 2 and then move to x equal 5, what was the change in my position? And you say 3. How did you do that? Because instinctively we know that the change is, we mean the subtraction. So we end at some position 2, some different x coordinate. We started at x sub 1, some earlier coordinate. And the displacement is the difference, the subtraction. Okay. The other flavor of changing position, motion described that we said we were going to define is distance traveled, which is sort of exactly what it sounds like. How far, if you tracked us during the entire motion as we go from position x1 to position x2, how long is that squiggly line that represents the motion that we took? Sometimes, if we need a symbolic variable for this, we can sometimes use s, lowercase s. It won't come up too often, though. Usually we'll just use the words distance traveled. Okay, great. Suppose you and I start from here and go to there, but you get there first. It is intuitive with our human experience in the world that we want to say that you were going faster because your motion took less time. And that's the key. Faster is an idea that we can derive from measurements of space, displacement, and measurements of time. You got there first. Your motion took less time. So how do we quantify the fact that we'd like to say that your motion was faster? Well, yeah, faster. Let's define, again, a vector version. Like we did for displacement. If a quantity isn't vector, by the way, then we call it scalar. Only magnitude, only a size, no direction recorded. Like the car odometer doesn't keep track of whether the miles we traveled were in the direction of east or north or anything like that. There's no directionality implied. It's just, this is how much ground you have covered. That's distance traveled, scalar quantity. All right, so we could do the same thing. Could be a little more precise with that idea. We've talked about changes in location, changes in position. We could talk about maybe the rate of change in position. That way we get to tie the new thing to what we said before. Changes in position, we're talking about displacement. Rate of change of position, we're talking about this new thing. And again, let's define a vector and a scalar version. Velocity is the word I'd like to use for the vector version. The rate at which our position is changing. I'd like to use the symbol V. Our position changed by delta x, the displacement. And it took some amount of time, delta t, for that change of position to happen. Elapsed time, I don't need to know what time it is. I need to know how much time has gone by. The change in time. If we just wrote t, that is if we compare it to just writing variable x is just a position, one. If we want to talk about the fact that some position has changed, well, that's delta x. Same deal with time. If we just write t, that's a particular time, like 1:32 and 27 seconds or whatever. If we'd like to talk about the fact that a particular motion took some amount of time, well, that's an elapsed time, a duration, delta t. Similarly, we could define speed using distance. Our speed, let's say, is the distance traveled, not displacement, divided by the elapsed time. So again, velocity is the quantity that has direction built into it. 10 meters per second east, that's a velocity. .65 miles per hour, that's just a speed, because there's no direction associated with that quantity. We have to be careful here. Suppose we talk about my commute to campus. Along the way, there are stop signs and traffic lights. I don't expect to always, all the time, from here to there, be covering ground at the same rate. Sometimes my tires are spinning faster than others. As I go, the rate at which my position is changing as I drive changes. Sometimes I have to stop. That doesn't really mean that we can't use this formula. Overall, I will have traveled the distance from my house to campus, and that's so and so many miles. And it'll have taken so and so much time. Never mind that I stopped along the way briefly at a stop sign or a traffic light or traffic on the Wilson Bridge or whatever. There are two related but distinct ideas here. One idea asks about the overall. For an entire duration, altogether, how much distance did you travel and how much time did that take? So we're sort of painting broad stroke over the entire motion altogether on average. We can make a distinction between the average speed over an entire time period. And then if I'm driving and I look down at the speedometer, we haven't talked about the speedometer yet. I look down at the speedometer and it says 35 miles per hour. That's not, the car doesn't know about the whole trip. It's telling me how quickly is my position changing? What is the rate of change of my position right now? At this instant, at this moment in time, never mind the duration, but right then, when we look down at the speedometer, our position is changing at a rate of 35 miles per hour. That might be the only moment in the entire trip that the car speedometer actually reads 35 miles per hour. Maybe there's traffic the whole way and it's stop and go. And there's the one moment where we actually get up to 35 miles an hour. I hope that's not the case. On average, all together, my average speed for this trip will be less than 35 miles an hour because I was going slower most of the time. But right then, my position is changing at a rate of 35 miles per hour. A picture, I think, would help. We are discussing the difference between average versus instantaneous velocity, the velocity at an instant. A picture. Suppose we had a stopwatch and we watched a car pull away from the stop sign here at the intersection at the corner of the street. Every second, we made a little mark on the road where the car is at that second. And then the next second, we mark on the road where they are, and then again and again. Let's make a graph. Let's do 5, 10, 15, 20, 25. Let's graph the distance from the stop sign in meters on the vertical axis, and let's graph time going by on the horizontal. 1 second after the car pulls away from the stop sign, let's say they are 5 meters away. 2 seconds after, let's say they're only 8 meters away. 3 seconds, let's say they're, I don't know, something like that maybe. 5 seconds, let's say they're already 30 meters away. If we talked about intervals, suppose we had these coordinates. 2 seconds, 8 meters, 3 seconds, 13 meters, 5 seconds, 32 meters. on average, how fast did we go during the third second? All right, so the first second that we spend is this one. The second is this one, and the third is this one. Our velocity or speed, so we're only going in one direction, so there's really not much disagreement between the two, except that velocity cares about direction, which we know is away from the stop sign and down the street. Let's talk about speed just to be safe. We're not sure whether it's east or north or whatever. Average speed, let's say between 2 and 3 seconds after we start. Should be the distance traveled divided by the elapsed time. Distance traveled is, we end up 13 meters. We began this interval at 8 meters. And this all took 1 second, from 2 to 3 seconds after the beginning. We could write it 3 seconds after we started the clock, minus 2 seconds, the final time and the initial time of this interval in question. So the numerator is 5, the denominator is 1, and we divide and get 5 meters per second. Okay. What about the next second? Same relationship, just different measurements. So we end up at 32, oh, I'm sorry, between 3 and 5, because I don't have a coordinate for 4. We end at 32 meters. We began this particular interval at 13 meters. We end the interval time-wise at 5 seconds. We started it at 3. (32 minus 13 is 19. Five minus 3 is 2. (19 divided by 2 is 9.5 meters per second. So let me get some color coding going on here. During the interval from 2 to 3, that's this one, we could track our motion. We go from that spot, that point on the graph, to the next one. During the next sort of segment, we can see that the blue segment is steeper than the red one. If we kept drawing the red one, it's clear that compared to the blue is increasing faster, increasing at a greater rate than the red one. That's instantaneous velocity. During the blue interval, as drawn at all times, the steepness, the slope, if we asked for the slope of this sort of curve, the operation that we would do is exactly the same as the operation we did. Apparently, the slope of a graph of distance or position versus time, the slope of a graph of position versus time is apparently velocity. The slope of a graph of position versus time is the velocity. And we can even be more precise. So that's true for intervals that we just considered, but there's a graph has a slope all the time. It's not particularly realistic that the steepness of this graph changes immediately going from red to blue. Our foot's on the gas, we're speeding up because we're getting faster, but it's probably going to happen smoothly. The actual sort of at all times, the continuous change in the position of that car might look something like that. Who knows? And we can use this picture to represent both average, because we've got these segments. We've got red and blue, and along those segments, on average, the slope looks like it does, looks like we calculated it. But we haven't said anything really about instantaneous. The slope at a particular instant, at a particular time of a graph of position versus time is the instantaneous velocity. And the way we can figure out what that is slope at a particular time. Well, at a particular time, I don't know how to calculate slope because no time has gone by if we're only talking about one instant. So what do we ask for? Let's Let's use this color. We ask for at a particular instant, at a particular point along that curve, we ask for the slope of the line tangent to the graph at that point. And that's the instantaneous velocity. So as we leave the stop sign, as we go along the street, our speedometer is that thing, the slope of the tangent line to a graph that we might make of position versus time. At each instant, we might look. The speedometer tells us at that instant how steep the tangent line is to our sort of path, our trajectory. If we wait and let some time go by and compare beginning to end, that's like red and blue, that's average. Because over some time has elapsed. Excuse me. All right. If we are, though, able to talk about the position we have at a particular time, we could edit what we wrote earlier just a little bit. Same idea. We could use functional notation. X is our symbol for position. At what time would you like to know the position? T2, the end of the interval in question. We've got to subtract the position we had at the beginning of the interval at T1. So now position gets to be an instantaneous quantity. You tell me the instant at which you'd like to know, and this is the thing that tells us where we are at that instant. We could use a similar notation the steepness of this graph changes. The slope of the graph is the velocity. So the velocity of this object changes. The velocity changes. Change in velocity. Delta, change in velocity v. Same story. Change in means take what we end with and subtract what we began with. How much have we added or taken away? The instantaneous velocity these are instantaneous because we're asking about particular times individual times. What is the velocity we have, the rate of change of our position at time t2, and what was it at time t1? Subtract, and that gets us delta v, the change in velocity from beginning to end of the interval. The last time we talked about a change in, the next thing we wanted to talk about was the rate at which that change occurs. Same story. The velocity change occurs in some amount of time. Some time has elapsed from t1 to t2. Looks like an E, A, C, C, E. I'd like to call this acceleration. The rate of change of velocity. And I'd like to use the symbol A. This, just like before, we're doing that. This kind of looks like the slope formula again. Change in thing divided by change in time, just like we saw a second ago. This is officially an average acceleration. So we could, I think you're thinking about it, we could also talk about an instantaneous acceleration and imagine it changing smoothly. If you'd like to do that, which we totally can do, we need calculus. Instead, let's restrict ourselves only to intervals of time during which the acceleration doesn't change. It's uniform or constant acceleration. If we do that, then that value the acceleration has during that entire interval is the value the whole time. And if we calculated the average, it would be that, because the whole time, that's exactly what we were doing. It's like if we start the stopwatch and our speedometer in our car says 35 miles an hour, and it says exactly 35 miles an hour the entire time we're looking at the stopwatch, for that entire duration, our average speed will be 35 miles per hour because that's the speed we were traveling the whole time. If we do that trick with acceleration, that for this time interval, our velocity was changing this fast, at this rate, this acceleration. During a different interval, we could consider a different constant acceleration, but let's restrict ourselves only to constant acceleration in intervals. We'll say piecewise or interval constant. If we do that, then there is a small set of equations that relate these variables, these quantities of motion. We will use these many times. You don't need to have them memorized. We will use them. If we are considering an interval of time during which the acceleration is constant, or we can assume that it is constant, or like we can treat the acceleration as constant during that interval, then the first thing we could do is cross multiply this definitional equation for acceleration. This is a confusing way to write it. This and this are functional notations. The velocity at the end and the velocity at the beginning, whereas this is a multiplication, acceleration multiplied by a time interval. Let's not write it that way. Let's go back to the subscript idea. Now I think it's a little clearer. The only thing we have here is multiplication. And we could write it that way and be very clear. We're multiplying the acceleration by the elapsed time. In other words, we cross multiply here and here. And then we'd end up with delta V, but we can move one piece of it to the other side as well. We could do the same thing with the earlier relationship. For position and velocity. As long as we specify that we're talking about the average velocity during delta t, during that time interval. Well, what is the average velocity? Well, if the acceleration is constant, then the average velocity is quite literally the average of the beginning and the end. We have those two velocities, we add them, we divide by how many there are, 2. That only works for a constant acceleration. We can prove it if you like later. There are 2 more relationships that we could prove, that we could derive from these 3. Our textbook goes through that derivation, so I'll just list them here in the interest of time. If you'd like to see the step-by-step, let me know, we can do that. these are the 5. These are tools. We have these relationships in a drawer of the toolbox that we're slowly filling over the next 13 weeks. And anytime we have motion with constant acceleration, we can reach for this drawer. When these 5 tools are just always going to be in that drawer, they're always going to work for us. So why are there 5? Take note of which ones include which quantities. Suppose we don't know anything about how much time went by. This one doesn't ask us anything about a time variable. There's no t in this equation. We don't need any information about how much time goes by to use this relationship. Suppose we don't know the velocity with which we end the interval. Well, this relationship doesn't ask us for it. And so on. As we practice using these relationships, that sort of skill, that facility will build. Translating the problem into sort of physics quantities and matching up the quantities that are given or asked about with the quantities that our relationships, our equations ask about and interrelate. And hopefully there's an alignment there, that there is an equation, a relationship that will use what we know to find something we don't, and doesn't ask us about things we don't know. That's what we will start. So I'll demonstrate how to kind of go about that in the demo activity, and then we'll practice that in the progress activity. All right. That's it for this video. Thanks, folks.